I'm Joe Savona. I'm on the React team at Meta, and I do not have a UI equals function of state in this talk, so I've got to do the next best thing. In this talk, I'm going to do a deep dive into the world of React performance. On the React team, we take a holistic approach to performance, looking at the big picture of where time is spent in applications. And then we develop features and APIs accordingly. This is why, as Rick discussed in his talk, we added support for concurrency. Concurrency helps optimize our apps, whether they're I/O bound, CPU bound, or both. But in this talk, I'd like to zoom in a little bit more on rendering performance specifically. As part of developing React compiler, we wanted to thoroughly understand exactly how well React is doing on rendering performance. You hear a lot of things online, and as we all know, a lot of things we hear online are not necessarily true. So we wanted to get a really solid understanding for ourselves. So we kicked off what has turned into a multi-year exploration into React rendering performance, and that has meant diving into the world of incremental computation. For those who aren't familiar, incremental computation is an umbrella term for software systems that can efficiently update their outputs when their inputs change. Common examples are things like spreadsheets. You change one cell, only the cells that are actually use that update. Build systems, and UI. React is an incremental UI system, despite what some folks might claim. Now, our approach on this was to create a series of benchmarks that are representative of different real-world scenarios. One of the challenges with benchmarks is obviously that you kind of end up focusing on one specific case, and we don't want to over-optimize because that's not representative, that one case isn't representative of all apps. So we created a whole bunch of different benchmarks. For this talk, I'm going to focus on just one, but I'll share kind of some of the broader results at the end. The draw benchmark that I'm going to focus on here is a highly simplified, can't emphasize the word highly simplified enough, prototyping app. I don't know why we didn't call it prototyper, we called it draw, anyway, we're not good at naming things. It supports creating text labels and boxes, and that's about it. And the UI is very simple, it's designed to be automated. Now, right away, there's a very, very important thing we can take away from this. Yeah. So for this benchmark, we have a script, as like I said. This is designed to be automated. We have a script that drives all the interactions to create the React logo. My colleague, Jan Cassens, actually took the SVG file and was able to extract out the commands from that to actually write this. Yeah, it just keeps on going. So we're gonna skip ahead a little bit. You get the idea. It's a logo. Now, might be hard to tell in there. That was actually to create the full logo at that resolution is 5,000 interactions, simulating clicks, simulating typing in the width and height fields, changing the X and Y positions. 5,000 interactions to create that logo. Now, the way the benchmark is set up is that each interaction synchronously updates the DOM, but we don't yield to the browser. So there's no layout or paint happening. So when you actually run it, so I was kind of running it in a mode just to let you see what's happening. When you actually run it, you click run, and the browser appears to hang for a second, and then all of us, you just see the finished logo, right? Because we're just going to do layout and paint once. In other words, this is measuring pure framework performance. Right, that's the whole point of this. Is we just want to see how fast can we make those updates. Okay, so we're computer scientists. We can set up an experiment, and the one thing I remember about experiments is that I'm supposed to change one variable at a time. So let's change one thing at a time. Well, what are the variables to choose from? In an incremental system, there are kind of two key architectural choices: the data model and the update algorithm. So for the draw benchmark, we chose a data model approach that a lot of folks in the community have asked about. We stored all the state, all the data for the app in a single state value, and then passed that down via context. So each component reads the data for its entity from context, and then accesses whatever properties it needs. Right? You might have heard about context, the idea of context selectors or things like that. This is kind of the rough idea, right? We're just going to have this giant pack of data in context, and we'll kind of pluck out at each component what we care about. At the app level, we're going to set this context, and then just pass down the ID to each entity, right? So that it can in turn go actually read this data from the context. And again, this is just a giant hash map stored in state and then set as the value in context. Okay, so that's our data model. As we can see, this is basically a giant stress test for state and context as the representation for all your data in an app. How fast can we make it? So this is the variable part of our experiment. So we chose to experiment with different update algorithms given the same data model. React compiler, and well, we'll get to the other ones in a second. Let's just look at the results for these two first. So our hypothesis was that React compiler should, hopefully, fingers crossed, we spent a lot of time on this thing, be faster. But it could only be so much faster, right? Because we're changing the context, and every single component pulls from that context. So how much faster can we really get when every component has to update, at least somehow, right? Okay, so baseline, first the results for React. Now this version has minimal manual memoization. And remember, this is 5,000 interactions taking just shy of 4 seconds on my laptop. And here's the result for React compiler. Yeah, not bad, right? We were pretty happy. Like, whew, okay, we can probably keep our jobs. So that's awesome. How, though? What exactly is happening? I just said every component has to update with this new context. So how did it actually get faster? So in React, when we render our UI, React creates a tree of what we call fiber nodes. The fibers correspond to components. So you've probably seen diagrams like this in the past. And our mental model is that, oh, the component is re-rendering. Right? So if draw updates, then we have to propagate that value down, and that means updating everything. Well, with React compiler, that's not really what's happening. For example, we only have to rerun the map if the entities change, right? If some other property of context changes, we don't have to rerun the map operation, right? The compiler is actually splitting up this component into smaller pieces of logic. And actually, we do the same thing on the item too, right? Breaking it up. So for example, we only have to update the style property maybe if the width and the height of that entity have actually changed. And then of course we do this for all the other components. So in the benchmark, if we've updated a single entity, sure, the context invalidates, the entities invalidate, we have to rerun our map, but then most of these entities are just going to be a no-op, and things basically stop there. And we actually spend time updating here. So as you can see, as the number of entities grows, we're just mostly skipping the work for all those entities and just focusing on where we need to. So this is how React compiler is able to make this type of application faster. So, first takeaway, React compiler can significantly improve the performance of context-based apps. Now, this is going to be a recurring question in this talk. Can we go faster?
Yes.
She's cheated. You saw the dry run. Doesn't count. Now, there's been a lot of noise about signals in the community. What if we use signals? I heard they're fast. So we built a prototype, a brand new approach to React, ground up rewrite of the runtime using signals. Or well, not quite signals, close. Pull-based or lazy incremental computation graph. We extended React compiler to emit the code for this, translating existing React components and hooks to use this new runtime. Pretty cool, right? I'll talk about how this works in a moment. Signals. We've heard so much about signals, and I'm sure you are all really, really excited. Are you excited to see the results? Want to see the results? Okay. Yeah. I'm just as excited to show them to you, and not for the reason you're expecting. Our results so far. Yeah. So this is when we started to question our life choices. Maybe we're just not cut out for this. And then we regained our senses. And we double-checked. OK, what if we just made a mistake? Because, that happens. So we took a signals-based virtual DOM-less library that scores well on popular benchmarks. And we ported draw to that library. The specific library doesn't really matter, as we'll see in a minute. Again, this is an experiment, so we're changing one variable at a time. So we're going to change the rendering algorithm, which means keeping the data model the same. So we use the same approach, state, passed down via context. And I want to call out, if you were to go and use a signals-based library, this isn't how they'd recommend storing your data, right? And so you might say that, oh, this is an unfair comparison. But the whole point is we're doing an experiment to compare, given this data model, what performance characteristics do we see given for this rendering model? So, how does it look? OK, maybe they're really fast, right? Signals are fast. All right. Our results so far. Wait, that wasn't. Oh, huh. So what's happening here? Well, in both our incremental prototype and in a typical signals graph, you end up with something that looks very vaguely like that. I got tired of drawing boxes and aligning them, so I'm sorry. That's the best you get today. On the left, we have our context, which really there's a state going into the context, but you get the idea. There's one giant input, and then we have a whole lot of derived computation. And then over here on the right, we have our places where we're going to use these values in our UI tree. See, it looks sort of like a tree over there. So to propagate a change, we need two phases, because these nodes in the middle, we only want to compute them once, right? If a node has two inputs, we don't want to compute it twice, first with only half of the inputs updated, and then again when all the inputs are updated. We want to make sure we compute each node at the right time, only when its inputs have been updated. So there's a very specific set of nodes in this case. You need to pay close attention to this, that are affected when this context changes. So watch closely. It's all of them. OK, so first we'll just mark them as changed. We're not actually recomputing here. We're just marking them as changed. And then we'll go walk this tree and say, give me the latest value. And so we'll actually pull back along this tree. And so that if there's a fancy algorithm here, you actually want to go depth first. And then if one of the nodes doesn't change, you kind of stop. And it's fancy. You can look it up on blog posts and stuff. But maybe ChatGPT can explain it to you. We're just going to skip over the high level here. But the point is, we're actually visiting the graph again. So we're visiting the whole graph, once to mark things as changed, and then once to recompute. So once you start thinking about it, you're like, that actually doesn't sound fast, does it? OK. So the signal-style pull-based approach wasn't getting us the performance that we wanted. But again, can we go faster? We actually got to the point that I just described a couple years ago, before we even shared React compiler at the conference last year. The existing incremental computation literature wasn't getting us faster, but we have a lot of experience with incremental systems at Meta. In my 11 years at Meta, I've worked on Relay, which is an incremental in-memory database, Relay compiler, an incremental compiler for GraphQL, Skip, which was an entire programming language for incremental computation. The compiler for Skip was, guess what, written in Skip as an incremental compiler, and now also working on this. And in addition, I've had the privilege to look closely at other incremental systems at Meta, like Hack and Flow. And one thing that has stood out across all that experience is domain-specific approaches can often outperform generic incremental approaches. Signals are a very general-purpose algorithm for incremental computation, but we can do something a bit more fancy. So fast forward at least a year. Numerous prototypes created and thrown away with gotta say, amazing engineering work, incredibly clever designs that just did not pan out until we hit upon a variant that we're calling React Fur. It's a novel approach to incremental rendering that uses a hybrid eager-lazy algorithm. Now, it's important to note this prototype does not support all the features of React, but it does support a lot of common patterns, more than enough to render the draw benchmark. That said, before you get too excited, this is a constrained prototype. It is a long way away from shipping. But we wanted to see, if we do kind of strip things down to the core, how fast can we make it? And that was the idea here. So this time, you're probably excited for the right reason. Yeah. A couple years of work to get there. We were pretty impressed, pretty happy. Now, a new React code name, a novel incremental algorithm. You probably have a lot of questions. You have questions? Yeah? Okay. I guarantee the one you're thinking of is not this. That's right, we're just gonna move right along. We gotta make things fast, people. We gotta keep going. So up until this point, we've kept the data model the same and experimented with just the different approaches to propagating updates. But what if we change the data model? So throw it all away, back to the basics, React compiler, a simple external store. What do I mean by that? Well, we'll define a store that looks something like this. It's got a get function to look up the current value of a drawing entity, a function to subscribe for updates to that value, and a way to publish updates to a few records at a time. And then we'll write a little hook that lets us read and subscribe to this store. Basically, I'm writing my own use sync external store here. There's a bunch of to-dos, but you get the idea. All right, so again, our results so far. And now, oh wait, that's right, I forgot. So note, this is a comparison now. We've broken the experiment, right? Because the whole point of the experiment is you change one variable at a time. We're changing the wrong variable now. So this is not an experiment, this is just a comparison. But still, what are the results? Oh yeah. And we barely, we slightly rewrote things to use a store, but we're not like dramatically rewriting the code. And in particular, because of the subscribe function, we can do very targeted updates in this store. So why is this so fast? Well, if we go back to the incremental computation graph that we looked at for kind of the signal style graph, the issue was that the context was kind of upstream of everything. And so when that changed, too much work downstream got invalidated. When we shift to a store, it's kind of like we can see inside that context. And so now when one entity changes, we're just invalidating way less work and doing a lot less downstream. But we're far enough along in the talk that you know what I'm going to say next.
Can we go faster?
Yeah, there you go. All right. In particular, what if we combine these ideas? Because I just said when we change the rendering algorithm and we change the data model, I'm like, can't you do both? You can. So React Fur, similar external store. Here's where we are so far. Yeah. I did not believe that number when I saw it. Really hope it's right. Okay, now this is the point where we have to go back. Remember how I emphasized the highly, like triple, highly, super simplified at the beginning of the talk? This is a highly simplified benchmark that makes it really great for optimizing the innermost workings of the rendering algorithm, but it also makes it less representative of real-world scenarios. So we also created other benchmarks that have a richer set of components and a more realistic data model. The draw was basically a key value store, as we saw. Now, these other benchmarks are, again, not all the way to a real app, but they're much more representative, and the results there were not quite as good. So this is a different benchmark, again, with React compiler in a store, and then React Fur in a store. And we can see that it is still a performance improvement, but not quite the same magnitude as we were seeing on the draw app, right? This is just as we increase the complexity of our app, the rendering algorithm just becomes less critical to the performance. And there's just only so much we can actually make faster. And there's another aspect too. Yes, it's faster, but it's not the full React. All right? And from a couple of years of experiments, we know that adding back some features that people rely on every day with React would, or at least could, eat into these wins. All right, but what am I asked next? No, it's time for a break. Okay, there's so much more that I wish we had time to get into, but let's kind of wrap up. So, first, key takeaways. We've seen that the data model is just as important, maybe more so, than the particular incremental algorithm we choose. Second, our results suggest that domain-specific approaches to incremental computation can be substantially faster than traditional incremental algorithms like signals, which are pull-based or generally lazy. But also, as we saw with that last slide, improvements on one benchmark don't necessarily translate to other benchmarks. And in some cases, or even if they do, they don't translate to the same magnitude, right? The draw benchmark is almost too simple, and a richer set of benchmarks stresses more cases. Worse, during those couple of years of experiments, we had actually identified a few different ideas that looked really promising on benchmarks. When we ported them to real apps, the wins just disappeared. And so ultimately, these numbers, we really have to actually push them further to get into a real app and see how things are gonna play out. So, what does all this mean for building fast apps? Well, it means using React to take advantage of all the performance features that we've built. First, as Rick showed earlier, we can use transitions and optimistic updates to ensure that we stay responsive, regardless of the library you use. Even if you're writing native code, for mobile, for example, you will run into situations where it just takes more than a frame or two to render a very complicated surface. Not to mention, you can be waiting on a network. So transitions and optimistic updates and things like suspense allow us to quickly respond to the user while preparing content in the background. Second, bound updates to what's visible. Use virtualization and the new activity component that Mofe showed to avoid wasting time on components that aren't even visible to the user. So many benchmarks out there will do things like updating 10,000 rows. You can't fit 10,000 rows on your monitor. Don't waste time updating them, right? Bound work to what's visible, and that will help your app stay fast. Finally, where appropriate, carefully consider the data model that you're using for your application. Good data modeling is critical for achieving peak performance. Now, if you've tried using an external store with React today, you know that it can be a little bit tricky. Use sync external store can de-opt out of concurrent rendering. So inspired by the research I've shared here, we're actively working on a new API to support concurrent stores. Specifically, we want to support concurrent stores that can do very targeted updates, which, as we saw, were so beneficial to performance. That's all I've got. Thank you.